This is a production of Cornell University.
So today, as Tony mentioned, I'm going to talk a little bit about my work on organic no-till soybean systems. So I don't have enough time to share all of the work that I've been involved in over the last 2 years, but I wanted to at least introduce you to some of the projects that I have been working on at Cornell. And really, I've been involved in 5 main projects that we can organize under 3 main topics or themes. So the first one is winter cereal thermal models. So we're working with cereal rye, barley, and triticale, 12 cultivars across those species. So this work is in New York as well as in Maryland, where we're working with Stephen Mirsky at the USDA. So this is really going to help us predict phenology and cover crop biomass.
I'm sorry, but can you speak a little louder?
Speak a little louder? Yes, I can. I will try to. Thank you. So we're also working on the trade-offs, looking at the trade-offs between forage quality and yield for winter cereals that are grown as forage double crops, so double cropping systems that dairy producers might be employing on their farm. And so this work is with Corrine Ketterings and a really big group of extension educators and farmers. We have a lot of sites throughout New York as well as Maryland. So it's been a lot of fun to work with such a big team. And then finally, my last 3 projects really fall under the umbrella of these cover crop-based organic rotational no-till soybean systems. And so that uses a roller crimper, which you can kind of see this implement on the front of the tractor here. It's used to terminate the cover crops, so roll them down flat, and I'm going to talk about this at length. And so these projects range from system economics all the way to a focus more on weed ecology. And so today I'm going to talk about one of these projects where we're looking at mixtures of barley and cereal rye to enhance weed suppression in these systems. And these aren't just disparate projects. There is a common thread here, and that's that they all involve winter cereals. So either as a cover crop for weed suppression or as forage for dairy producers. So other than a really long name, what is cover crop based organic rotational no-till soybean? Some of you might not be familiar with this system. This photograph is from the Musgrave Research Farm in Aurora, New York. And so what I've highlighted here, this is how you would typically prepare the soil. So you have your primary tillage, your secondary tillage, and then you can come in and plant, for instance, your soybean crop. So in contrast to that, with these cover crop-based systems, you need to start with a cover crop in the fall. So what you're looking at here is cereal rye and barley. This would be planted in mid-September. And then when it reaches anthesis, so mid to early June, so I should say mid-May to early June, they're ready to be terminated with a roller crimper. And that's what it looks like after that roller crimper is passed over those cover crops, forming a nice thick cover crop mulch. That provides your weed suppression, and then you can no-till plant through that cover crop mulch for these no-till based systems. So we've established you have your tillage-based management and then your cover crop-based no-till. And so why would farmers be interested in this different type of soybean production? If you think back to 2013, we had a really wet June and August in the Northeast. And if we look at a photo from Aurora, you can see a lot of surface erosion washing out of the soybeans here in these tillage-based systems. And then plots adjacent to it, you can see that the soybeans are growing up undisturbed through this thick cover crop mulch. Later on, surface sealing of those clay soils, you see standing water, and then again, this cover crop-based system is just fine. And so this is one of the main reasons farmers are interested in this system, and that's from a soil health perspective. So in addition to reducing erosion, a lot of research has looked at increasing biodiversity, so both below ground and above ground, obviously associated with reduced tillage or disturbance in these rotational no-till systems. When we think of system advantages, it's really for conventional and organic growers. So for a conventional grower that might be struggling with herbicide-resistant weeds, we can think of this as an integrated weed management approach. So in a really simplified way, you can think of these cover crops as replacing your synthetic herbicides, and for organic growers, that would be replacing your cultivation. But of course, these cover crops provide many other benefits. I forgot to mention here, when you're comparing it to tillage-based organic production, we see about a 30% reduction in diesel fuel and labor. And what's interesting, when you talk to farmers at grower meetings, they're really drawn to this from a soil health perspective. We can talk about energy savings, but it's really about reducing tillage in their crop rotation. And that's what's really driving them towards adopting this type of management system. So this all sounds pretty good. You know, is this the new perspective for farmers? When you're sitting on their tractor, you've got the roller crimper out front, looking at a field, a winter cereal's ready to roll that down. I mean, we hope so. That's what we're working on. We're working right now on a farmer manual to help address some of these issues that farmers are coming up against. So issues related to weed suppression in particular. And one of the most common questions that we get at grower meetings is, how does this fit into my rotation? Farmers are typically planting, if you think of a corn, soybean, wheat rotation, soybean would be following corn grain. And so for this system to work, they would be establishing a winter cereal like cereal rye after they've harvested corn grain. And that's going to be really late in the fall and is not going to provide enough biomass or a uniform stand for weed suppression. So right off the bat, that's going to be a real problem for farmers if they're stuck in this corn, soybean, wheat rotation. So from my perspective, I'm interested in kind of a food grain-based system. It might have more small grains. So something like wheat would be a really good crop to precede this. So wheat's going to be harvested in August, and it gives you lots of time to establish something like cereal rye in early September. If you're working on a feed grain-based system, a short season corn silage would work, and that's going to push you maybe into mid-September for establishing that cover crop. And what I want to draw your attention to, if you look at these later planting dates, so these are 6 different cereal rye seeding dates. These photographs were taken on April 1st. And if you notice at these later planting dates along the bottom, you see a lot more soil between those rows of cover crops. And where you see exposed soil, that's where weed seeds are going to germinate. And that's a real problem because in this system, it's those early emerging weeds that really dominate. So you've got wild buckwheat, common ragweed. They're going to emerge before you actually roll that cover crop in late May. So as you can see here, they've come up in that stand. In this case, it's cereal rye in the background here. So if you look at some of these data from Pennsylvania, you can see common ragweed here in these violin plots emerge a lot earlier than other common summer annual weeds. So that bulge in this plot here indicates that the majority of that species is emerging, in this case, in early April. In New York, we would expect this to be a few weeks later, but that's still going to be the majority of them emerging before we roll down these cover crops. And so that's a real problem because common ragweed emerges early, and it also can survive rolling and crimping. And this has really informed a lot of our research. This is not just a phenomenon on the Musgrave Research Farm. This is throughout the Northeast. This common ragweed just dominates in these cover crop-based no-till soybean systems. So in terms of previous research, the focus has really been on maximizing cereal rye biomass. So manipulating seeding date and seeding rate and a couple other factors like that. Emerging from that has been this threshold of 8,000 kilograms per hectare, and it's been suggested that if you can achieve that, you're going to get consistent or adequate weed suppression throughout the season. But there's some problems with that, with this excessive cover crop production, and that's lodging, which you see here, in really fertile soils, and it's also really difficult to get good seed to soil contact. It's really hard to get good soybean seed placement through a thick mulch. So in this photo here, you can see that they've added sandbags on top of these planter units to try to get more down pressure so you can actually penetrate that thick cover crop mulch and get good seed to soil contact. And this is particularly challenging if it's dry in the spring. And later on, obviously, if you don't get that good soybean seed placement, germination is going to be poor, and some of these soybeans that do emerge, as you can see, are pretty chlorotic, and you're going to see a yield loss. So for our research, and the way it differs from all this previous research, is that we're moving away from a focus on this maximum biomass, and instead we're focusing on optimizing early season shading for optimal or for better weed suppression. And so to do that, we're looking at mixtures of barley and cereal rye. So cereal rye is tall and slender, barley is going to be shorter, wider leaves, and I'm not suggesting that this is really a true niche differentiation as you would expect with a legume and a cereal, but these slight differences in phenology, stature, and leaf architecture might be enough to give us that edge to provide better early season shading. So we've got a couple objectives. We're interested in the impact of these cover crop mixtures on weed suppression as well as ultimately on soybean yield. And then we're looking at 2 main management treatments, so high residue cultivation and then just standard no-till. And again, we're looking at those effects on weed suppression and soybean yield. In terms of experiment design, we used a split block design, so replicated 4 times over 2 years. This was 2012 to 2014 at the Musgrave Research Farm. We seeded our cover crops in a replacement series. So you've got a barley monoculture, a 50-50 mixture, and then a cereal rye monoculture. And these were seeded, as I mentioned, mid-September at 19 centimeter row spacing. I will note that I have some photographs in here from 2013, but all the data I'm going to share is just from 2014. I really just have time to share a subset of all the different treatments that were involved in this experiment, so we're just going to simplify this in the interest of time. All right, as I mentioned, you've got your two management treatments, standard no-till, which is going to involve rolling and crimping that cover crop when they're at anthesis, and then no-till planting soybean on that same day. And that's it. You don't have to do anything else until you come in and harvest that soybean in October. With high residue cultivation, on this about 2 to 4 weeks after you've planted that soybean, you're going to have a single pass with a high residue cultivator to control some inter-row weeds. And this is one of the reasons why we use these wider soybean spacing, so 76 centimeter rows, so that facilitates the operation of this high residue cultivator. And we did include, adjacent to those plots, an inter-row cultivated treatment, and so this allows us to compare these cover crop-based management practices to what would be kind of your traditional tillage-based soybean management. So to look at this roller crimper a little more closely, it basically involves a cylinder with these blunt metal blades welded in a chevron pattern, and it's going to bend or crimp these plants at their base, as opposed to shearing or cutting them off as a mower would. And this is an important distinction because we want that cover crop mulch to persist throughout the season. And when you mow these cover crops down, which has been looked at in other research, it's of course going to increase the surface area, which is going to speed up decomposition, which is going to result in poor weed suppression. With the high residue cultivator, after those cover crops have been rolled, this implement has really wide sweeps on it that are intended to slice through the soil just below the soil surface. It's going to sever weed shoots from weed roots, and it has really thin shanks with the intention of limiting the amount of residue that's dragged all over the field. So this photo kind of shows that we had some trouble actually calibrating this equipment. We didn't get enough cover crop biomass, and you can see some soil that's actually turned up between the rows. Ideally, you wouldn't see anything. You'd barely notice that this piece of equipment has been run through the field. In terms of seeding rates, we based our replacement series on a rustic rye, and then we adjusted for differences in size and mass for the barley seed, which is why we refer to this as density-based seedings as opposed to volume-based seedings. So this low density is equivalent to about 1 bushel per acre, and then this high density is 2 bushels per acre. You'll notice with the soybean, this is a really high seeding rate. This is about 300,000 seeds per acre, which is about double conventional soybean seeding rates. And if you think about herbicide-based conventional soybean production, these are essentially weed-free systems, with the exception of issues with herbicide-tolerant weeds. So you're going to have really high germination rates for the soybean, really good seedling survival, obviously very little to no weed competition, and so you can use those lower soybean seeding rates and still get maximum yield. But for us, this is really part of our cultural weed management. So we use these high rates to achieve canopy closure earlier in the season, which is going to provide greater shading, which is going to reduce the fecundity of weeds, so some of these later emerging summer annuals. So in other words, less seed production from some of those later species. So this, in concert with that rolled mulch, really forms the basis of our weed suppression. And this photo is a little bit dark here, but what you're seeing is a shot from underneath that soybean canopy here that's completely closed. You just see a little bit of sunlight filtering through, and then you see that nice rolled cover crop mulch there along the soil surface. In terms of sampling, before those cover crops were rolled, we measured cover crop biomass and population, photosynthetically active radiation, or light transmittance through that cover crop canopy. And then after they were rolled, weed identification, we looked at weed biomass, and then also soybean density and yield. We certainly measured a lot of other things, but again, this is just a subset of this experiment, so this is what we're going to focus on. So if we look at the interspecific cover crop competition, we've got cover crop biomass on the y-axis and those replacement series, so that seeding ratio along the x-axis. And you've got your low density and high density seeding rates. And what you'll notice here in the low density is that, I should first mention, these dashed lines are your barley monoculture, and these dotted lines are your cereal rye monoculture, and then the solid lines here are your 50-50 mixtures. And so what you're seeing here is what we term over-yielding. at that low density. So in other words, this is a higher absolute yield in that 50-50 mixture of barley and cereal rye compared to a cereal rye monoculture or the barley monoculture here. And with these studies, typically that's what you're looking for. Maybe if it's a legume and it's a cereal, you want over yielding, especially if these are being grown for grain. But for our purposes, we're really more interested in shading. So does this higher biomass here actually translate into enhanced shading and thus better weed control? And I'll also just note we actually didn't see that in the high density. And there's a number of different reasons here. Perhaps the cereal rye has greater competitive ability, especially in what would be considered a more resource-limited environment. So when we look at par transmittance, so that light that actually is making it through that canopy, we have the same seeding ratios along the bottom. We actually don't see enhanced shading in that 50-50 mixture. So instead, you see that par transmittance increases as the proportion of cereal rye decreases. So in other words, at that cereal rye monoculture, that's where you see the least amount of light reaching the soil surface. And in that barley monoculture, that's where the greatest amount of light is actually making it through. And when you look at weed biomass across those seeding ratios, you see a really similar trend as you might expect. Of course, if there's more light coming through the canopy, you're going to have greater weed germination, higher weed biomass, and of course, less weed biomass when there's less light making it through the canopy. We saw this really clearly in the field. You have your barley monoculture here, and that is a lot of common ragweed that's emerged. So we really did not have nearly enough biomass production there, or of course shading to suppress those weeds. With the cereal rye monoculture, we had actually pretty good, pretty adequate weed suppression throughout most of our treatments. When we look at total weed biomass, you can see that common ragweed comprised over 80% of that biomass, so it was really dominant in this system. We had foxtail species, so yellow and giant foxtail made up about 8%, and then a variety of other weeds made up the remaining 10% for this experiment. So if we're going to then focus on common ragweed, let's look at those management treatments. So we've got common ragweed biomass here. You've got, let's look at the difference of high residue cultivation and standard no-till. And what we saw was about a 20 to 30% reduction when you integrate that high residue cultivation. And of course, you can see by the error bars, this wasn't a significant reduction, but if you think of this from a farmer's perspective or a more applied perspective, reducing common ragweed biomass by a few hundred kilograms is going to be really important for long-term weed seed bank management. So there's going to be a lot lower contribution of weed seeds that are going to be a problem later on in their rotation. And this photo is from 2013, and I just wanted to use this to illustrate how effective that high residue cultivation can be. So these lighter rows here are soybeans that are ready to be harvested, and what you'll notice in the standard no-till, all these dark patches here, all of that is common ragweed. And so when you look at the high residue cultivation, you can see no common ragweed at all in between those rows. So under certain conditions, this can be really, really effective at taking care of that inter-row common ragweed. All right, and here what we're really interested in is shading a really good predictor of common ragweed biomass? So you've got common ragweed biomass on the y-axis again. We have cover crop biomass, so combined both barley and cereal rye biomass here, and then par transmittance on this right side chart. And so really you can think of this as a lot of the previous research is focused on this relationship, just maximizing cover crop biomass, whereas we've shifted the focus over here to par transmittance or shading. And what we found, both in the low and high density treatments, as well as all the other treatments I couldn't discuss, was that in fact shading was a much better predictor of common ragweed. So you can see here, we definitely had higher R-squared values when we look at this relationship. And what's interesting to note is, as we saw with the low density and that that over yielding in that lower density treatment, high biomass production doesn't necessarily result in greater shading. So it definitely suggests to us that we really need to focus in on shading to really tackle this issue of early emerging weeds like common ragweed. In terms of soybean yield, we actually saw no differences between seeding ratio or management treatments, which was surprising given the differences in cover crop biomass as well as weed biomass. And on average, we got about 40 bushels per acre, which is actually the lowest yields we had across all of our different treatments and our on-farm sites. We typically get 45 to 50 bushels, which is really competitive with other organically produced soybeans, so tillage-based systems. When we compare this to the in-row cultivation, we see about 80% of that yield. And so that's definitely a substantial yield loss there. Again, this is a little bit related to these were not very productive treatments for us. And of course, you need to factor in the fact that there's going to be a 30% reduction in diesel fuel and labor with this type of management. So in summary, we found that early season shading definitely was an important predictor or common driver of common ragweed biomass. But these mixtures of barley and cereal rye might not be the best way to actually achieve that enhanced shading. We're definitely encouraged to continue pursuing this because preempting that common ragweed biomass is just so critical for addressing these issues for farmers in the Northeast. We also found that high residue cultivation was really useful for controlling that inter-row common ragweed, and you can think of it as a rescue cultivation. And for long-term weed seed bank management, this might be a really useful tool. And then this is actually different than what we'd expected. Soybean yield was not higher when you integrated that high residue cultivation. And actually, in some ways, this might be a desirable result for us because what it suggests is if we focus on cover crop management, and so we can really suppress those weeds with just standard no-till, you're not going to see a yield loss if you don't integrate high residue cultivation. And really for farmers, they're not that interested when we've gone to grower meetings and talked about this in using a high residue cultivator because the whole purpose or their whole interest in this is a reduced tillage system. So this idea of high residue cultivation is not very popular. And we definitely see high potential profitability for this system. Like I said, if you get these competitive yields in combination with this reduction in energy use, this is going to translate into higher profits for farmers. And so with that, I'd just like to thank, in particular, Chris Pelzer, Brian Caldwell, and the rest of our lab, and all the folks at the Musgrave Research Farm. I certainly couldn't have done this research without everyone's assistance and support. So if there's time, I'd love to take some questions. Thank you.
This has been a production of Cornell University, on the web at cornell.edu.